So here's how these go. So we'll start off with the title, Related Rates. So it's all really built off of, you think of some mathematical formulas. Let's say like this one. What is equal to pi r squared? Area. Yeah, area is equal to pi r squared. Area of a circle is pi r squared. Now, let's say you had a circle. Here's the radius. And let's say the radius was actually, let's say it was getting bigger. Okay? Let's say the radius was growing at like, I don't know, 4 inches per second. So you've got a circle, its radius is growing at 4 inches per second. It's a constant rate. Okay? So radius growing at 4 inches per second. Another way to write like the radius is increasing at 4 inches per second is actually I could say that dr dt is equal to 4 inches per second. Dr dt means the rate at which r changes with respect to time. I'm not sure what that noise is. Like, and so think about it this way. Velocity is equal to d what dt? Velocity measures the change in what per time? Some of you are saying it. You're saying things like distance. Velocity is the change in position. Right? The rate at which position changes with respect to time, we call that velocity. The rate at which velocity changes with respect to time is called acceleration. So, I mean, just the big ideas here were, hey, you have this circle, okay? Its radius is increasing at a rate of 4 inches per second. Now we want to be able to talk about how do you suppose that the area is changing? Is the area, always changing by the same amount? Or is it? Okay, so you guys are pointing to the squared. You're saying, okay. So will the rate? Let's write this question out. Will the rate at which A changes, will the change in area with respect to time be larger when r is smaller or when r is larger? dA dt. The rate at which area is changing with respect to time. Rachel?
So it's getting larger because if you plug 4 inches per second into where radius would be, you get pi 4x squared, depending on how many times.
So are you trying to plug that 4 in, Rachel, in for that r right there? Yeah. Now see, the thing about that r, guys, that's the actual radius, not the rate at which radius is changing. The 4 is going to go somewhere. It definitely will.
It changes by that much per second, so wouldn't that be how much, you wouldn't put 4 in for the radius, but since that's how much it's changing, would you not attach it to like an x?
It's going to go in there. Yeah, I mean, you're kind of getting us to the next step. We start here and we say, hey, by the way, A and R are always related in this manner. No matter what, A is going to be equal to pi r squared. If two quantities are equal, the rate at which they change will also be what? Equal. Yeah. If Alex and I always have the same amount of money in our wallet, and I'm making $10 per hour, well, then Alex is also going to be making $10 per hour kind of thing. If two things are always equal, the rate at which they change has to be equal. If that rate were not equal, we wouldn't always have the same amount. So you can actually take the derivative of both sides with respect to time. If these two quantities are equal, the rate at which they change will also be equal. Anybody know what the derivative of pi r squared is with respect to time? Good. Okay, you're getting this 2 pi r. Good. Times r prime. And another way to write r prime is dr dt. Now, how did you know that r prime should show up? Because you know, like when we were doing implicit differentiation, somehow you knew when y prime should show up, and you always knew that x prime shouldn't show up. Has to do with the rate. Yeah, look at what you're taking. That t right there. You're taking the derivative with respect to time. What's your variable? Your variable is r. You're going to have an r prime show up. It would just be like, don't write these down, but let's say you had the derivative of x squared with respect to x is equal to how much? 2x. Now change that. Let's say the derivative of x squared with respect to s. 2x x prime. And another way to write x prime would be dx ds. So
wait, when you're writing out an equivalent that you don't have to really worry about the 1%, to worry about the top, what is changing?
correct. I mean, you want to pay attention to, you're taking the derivative with respect to what?
Yeah.
So when we came back up here, and I took the derivative of both sides with respect to time, pi r squared became 2 pi r r prime. Now what's the left side going to become? What's the derivative of a with respect to time? A prime. Okay. Now, we had a question down here. Did we ever make a prediction? Will dA dt be larger when r is smaller or when r is larger?
The same.
The rate at which area changes. Think it'll be larger? Okay. So we have this formula here that tells us how r changes. And tells us how a changes. Back at the initial prompt, were there any pieces of information that we could filter into this equation? I think we only started with one piece of information. And you already tried to use it, Rachel. What was it?
That's the 4 inches per second. We know that that's how r changes. And because of that, we know that it's r prime.
Yep. Yeah, r prime is your 4 inches per second. It's how r is changing. If r were decreasing in length, that would be a negative. Like if it were going down by 4 inches per second, your rate would be negative 4 inches per second. So we can rewrite this formula. A prime equals 2 times pi times r times 4. A prime is 8 pi r. Is a prime at all related to r? Does it depend on r? does A prime have anything to do with what the current radius is? Yeah, it's over there in the formula. Now check your guess. You guys said the larger R was, the larger A prime would be. Does this formula support that? Okay, cool. So that kind of gets us started. I'll do a more concrete example. Okay, so we're going to kind of shift gears, go to a different problem, but one that I think you can imagine a little bit better. We have a building. Okay, who can guess what? What is? What's that? That's definitely a ladder. Okay, definitely a ladder. Now, here's the thing. I don't know. Let's give that ladder a length. How long are those big extendable ladders? I don't know, what are they?
60 feet, 20.
We're going to go with 20 feet. All right, length of that ladder is fixed, 20 feet. Now, no, you don't have to draw this yet. We'll work through it. So, unfortunately, what's going on here is, if you've ever been on a ladder and the base starts to slide away, and you're on the top of the ladder, it's not really a comfortable feeling. Okay? So, what we're doing here, the base of this ladder is going to be sliding away from the building at a rate of, let's go with 0.75 feet per second. Now, yeah, it seems pretty insignificant right now. Now you're going, yeah, you have time to react. It seems pretty slow. But now let's say the top of the ladder. What's the top of the ladder do if the bottom is sliding out? Okay, it's going down. That's the question. Can you ask it again, Hannah?
Would the top of the ladder be falling down at the same rate as the bottom of the ladder would be sliding out? Yes.
No, it's a different rate.
That's the fundamental question. That one right there. Would the top of the ladder be sliding down at the same rate as the bottom is going out? So we're just saying, hey, we've got a ladder. The base is sliding away from the building, which means the top is sliding down at some rate. Can we find that rate? And is that rate constant? Is it going to be a negative 0.75 feet per second? Is that what it's always going to be falling at? Or does the rate depend on the position of the ladder, how far it is away from the building? Let's say that whoever's operating this ladder is not super intelligent and that this distance starts at 1 foot. I say not super intelligent because that's probably not a very safe angle. If you've ever climbed a ladder and you're up 20 feet and you've only got 1 foot difference between the base and the top, that's not going to be great. So what I want to know is, if the ladder is currently a foot away from the building, how quickly is it falling? And what would have happened if the ladder would have been, 8 feet from the building? Would it still be falling at the same rate? Faster at 1 foot or faster at 8 feet? You think faster at 8 feet? So here is the, let's say this is your building, this is your ladder. So I'll pull the bottom away at a constant rate. And you just figure out if the top's going down at a constant rate or when it's actually going faster or slower. Faster at the end? Okay, well let's find those rates, okay? Let's find those rates. So, first off, you got to start with your variables, okay? Let's see, I've got the length of the ladder, that's 20 feet. I've got a couple sides going on. I've got like this thing here, this part, and I've got this part. And let's do this in green. So, we need some variables. We'll call the yellow one X, and we'll call the blue one Y. Can anybody build an equation that relates X, Y, and 20? You got it. Okay, you want to always start with a relationship that holds true no matter where the ladder's at, no matter where your problem is. In the previous one, it was pi r squared. Does pi r squared always hold true for area of a circle? Yes. So start with some function that's always true. Always true. Now, what you don't want to do here is try to plug 1 in for X. Like if you took 1 right now, I'm saying 1 because it sits right here. If you took 1 in and plugged it in for X, and you solve for Y, what would you actually be calculating? Yeah, the height of the building, how high the ladder is up. That's not the question. So don't plug that in yet. So we've built a model here. We've built a function, but this function doesn't have anything to deal with rate. What's the next step?
You find the derivative of its position.
Find the derivative. Now, you're moving at 0.5 feet per second. So you're going to take the derivative with respect to time. So if the left side always equals the right side, then the rate at which they change is also always equal. What's the derivative of 20 squared with respect to time? How does 20 squared change as time changes? It doesn't. Yeah, and that's why we already had the answer of 0. Okay. What do you notice about the left-hand side? Does that plus make life any easier? Yeah, you can do 2 separate. What's the derivative of x squared with respect to time? 2x. Oops. 2x x prime. I'll write it as 2x dx dt. What about y squared? 2y y prime. 2y dy dt. That's y prime. Okay. So now you've got your model. Okay? It relates x and y and their rates. So, do we have any information that can be plugged into this model? Where's 0.75 go? That's just x prime. Yep, that's just 0.75 feet. That's just x prime. No, I mean I could have written it like this, or I could have written it as, this is probably more student friendly, 2x x prime plus 2y y prime equals 0.
That's what I was just kidding. Yeah.
So we'll work with that one. So you guys said 0.75 goes in for x prime. The original prompt was, hey, how fast is the top falling when you're 1 foot from the building? And then how fast is the top falling when you're 8 feet from the building? So those are the two questions we're trying to answer here. We do know that x is 1, which also sets up, it says if x is 1, we're going to know y because of the Pythagorean theorem. So if you've got x, you can get y, and that will just leave y prime left. So what I want you guys to do is, I want you...
Will that always be given to us? Like the one?
They'll have to give you one of them, yeah. Yep. So you have two different prompts here. You have the one in orange I want you to work on, and then you have the one, we'll go in green. And you're going to use this yellow piece to help you out. So I'll pause this and let you guys work on it. Alright, so you've really built two models that you're going to use. Okay, so we have this model which comes in handy. And don't forget, you still have x squared plus y squared equals 20 squared, so 400. So the first thing we're going to answer is, hey, by the way, when x equals 1 and x prime equals, how much was it, 4? 8. What was the rate at which x was changing? Oh, 0.75, okay. And that was like feet per second. It was y prime equals question mark. All right, well, if you noticed with what we have in yellow there, if you're going to solve for y prime, you have to know both x and y. So the x is how much? 1, and the y is radical 399, which comes from using this right here. So you'll just go 2 times 1 times 0.75 plus 2 times root 399 y prime equals 0. So you end up with y prime equals negative 2 times 0.75 divided by 2 root 399. I just moved this entire term over, so it became negative. So y prime equals, what'd you guys get? Negative 0.037. And what were the units on x prime? They in feet per second? So we're at feet per second here. So you'd go through the same process, and instead of using 1 and root 399, you're going to use, was it 8? 8 and root 336. Did you guys match up with that? 8 and root 336? Okay. So yeah, it changes your answer, and when you go through and you do it that way, see the first one was negative 0.037 feet per second. What was y prime for when x was 8? Three point. 0.3273. Anybody else come up with that? I said when x was 8, negative 0.3273. Alex, Did you guys get that second one? Did you get a different answer? You just didn't come up with it. Okay, all right, so what are your questions? What makes that difficult? Dylan?
Couldn't you have just put y prime on the other side?
Sure, like gone from the yellow and right away isolated y prime equals, what do we got? Negative 1.5 x over 2y. Yeah, that would have been a good.
Could you, I guess the top equation, just put in y include the 2, so that you could just do it from the x?
Yeah, so you could rewrite the top equation as, what would that be? Y equals the square root of 400 minus x squared. So it's a really good idea that he's got here. He says, hey, I think this is what you're saying, right? Solve this for y, and then actually plug it in, and now your function only deals with x's. Yeah, be a really efficient way to do it. Yeah, because you'd then have this model that you could put into your calculator, which I think is what Mackenzie's doing right now, actually. So it'd be a good way to do it. Okay, what else do you want to know? Rachel?
When is this applicable?
I can give you another problem.
Well, I just mean like, what kind of problems are we gonna see this in with calculus, like on the test?
Yeah, let me give you one right here.
Okay.
So let me show you a problem that you're going to need to utilize this. So here you go. See, yeah, these are AP test style of questions.
Actually, just gonna give us questions like the ladder.
Yeah. They're going to say, hey, you've got this situation. This variable is changing like this. This variable is this much. How is the other variable changing?
Okay, so they're just gonna be like, there's a ladder.
Yep.
And that's it. That's the question.
Yeah, and I'll write one here for you.
Oh no.
Okay? Yes.
Like, how do you know what, like, normal equation, like, before you know
That's
part of it?
That's part of it, yeah. If you guys didn't hear, the question was, how do you know which normal equation, like what's the base equation that you need to start with? And that's really hard. So you got to, I start it and I'm like, okay, I've got these variables, how can I relate them in an equation? And I think that's why they call it related rates. How can I relate the variables? Once you get them related in an equation, then you just take the derivative and you start plugging stuff in. Don't plug anything in until after you've taken the derivative of both sides. So here's another one. This might challenge you a little, but give me a second and I'll write it up. So here is the next question for you.